In this video tutorial, we'll be introducing the concept of enthalpy as it relates to physical, chemical, and nuclear changes. Before we begin, let's briefly review the laws of thermodynamics. They describe the fundamental behaviors and properties of thermodynamic systems. There are 4 laws in all, but in this course we will only be concerned with the first 2. The first law of thermodynamics states that energy cannot be created or destroyed. That's the law of conservation of energy. And that energy can only be converted from one form to another. The second law of thermodynamics is not exactly stated this way, but for our purposes, you can essentially think of it as saying when 2 systems come in thermal contact with each other, heat is always transferred from a higher temperature to a lower temperature. All right, and this continues until a dynamic equilibrium is established. So essentially, hot objects will warm up cold objects. You never see cold objects warming up hot objects. Energy moves from high to low. Now, enthalpy is a measure of the total energy of a thermodynamic system. Changes in enthalpy, delta H, are easily measured, but enthalpy, H, itself is not. In the end, though, the enthalpy value itself is unimportant because enthalpy change is what matters. So, for example, when you're climbing to the top of a building, you don't know how far away you are from the center of the earth, but you do know how far you climbed. The initial distance from the center of the earth is inconsequential. It does not make your achievement any more or less important. Alright, so for the purpose of this course, we'll be dealing with delta H, not H itself. So always write the delta symbol in the front to show that it's an enthalpy change and not the enthalpy value itself. Now there are some sign conventions that we need to take into consideration. Positive delta H means that energy is being added to the system, so it's an endothermic process. So let's say there's a chemical reaction occurring in a beaker, and I touch that beaker and it feels cold. That's because it's absorbing energy from my finger into the actual system, and that's why it feels cold. Versus negative delta H means energy is being removed from the system, so the system is losing energy. It's an exothermic process. So if I happen to touch a beaker where there's an exothermic reaction occurring, because it's losing energy, giving it away, when I touch it, I will feel that energy and it will feel hot. Alright, so endothermic reactions are going to be cold to the touch. Exothermic reactions are going to be warm to the touch. Now for the purposes of this course, delta H, delta E, and Q are all the same thing as far as you're concerned. It's just basically a change in energy. How much is being lost or gained by that particular process. Now there are several categories of enthalpy change, 3 of them that we'll be covering in this course. The first is physical change. The second is chemical change. And the last is nuclear change. During a physical change, the physical properties are altered, but the chemical properties for the substance remains the same. A common example is delta H solution, so the enthalpy of the solution. So you'll instead of saying delta H solution, typically they'll pronounce it as enthalpy of solution or heat of solution. It doesn't matter which term you use. In the end, we're just talking about the enthalpy change that occurs when a solute dissolves within a solvent. Now, during this process, the intermolecular forces, the attraction between solute and solute particles, as well as the attraction between solvent and solvent particles, must be disrupted, and that requires energy, so that's going to be a positive delta H value. At the same time, you will be forming new intermolecular forces between the solute and the solvent, and that will release energy, so it's a negative delta H value. Alright, so energy is required to break up the solute-solute attractive forces, as well as the solvent-solvent attractive forces, and that would be a positive delta H value. At the same time, you're forming new intermolecular forces between the solvent and the solute, so now there's a new attraction, and that will be a negative delta H. It releases energy. Now, if this process requires a lot of energy to break up the solute-solute and the solvent-solvent intermolecular forces, more than it would be releasing, then that reaction will have an overall net enthalpy change that is positive. And we say that the process is endothermic. On the other hand, if you release more energy by forming these solute-solvent intermolecular forces than you do trying to break up the solute-solute and solvent-solvent intermolecular forces, then the net enthalpy change is going to be negative, and the process is exothermic. It's just like a business. Every business must spend money to make money. If you spend more money than you make, you're going to go out of business. You're going to have a debt. If you make more money than you spend, then it's a very profitable business. Well, same thing. If you absorb more energy breaking up these intermolecular forces than you release, it's going to be endothermic. If you release more energy than you absorb, then it's exothermic. Now, if you recall, during a phase change, the temperature does not change. So over here we have the solid-liquid boundary, and this would be the liquid-gas boundary. So when we talk about the enthalpy of fusion or the heat of fusion, we're referring to this particular phase boundary, fusing liquid molecules into solids. If we refer to the heat of vaporization or the enthalpy of vaporization, we're talking about the liquid-gas phase boundary. Again, if you have a positive enthalpy value, we're going from solid to liquid because now we're adding energy in. So when you add energy into this phase boundary, you are melting. If it's a negative enthalpy value, then that means energy is being lost by the substance. And so when water loses energy, it turns to ice. That's freezing. So sometimes in a question, they won't tell you that a substance is freezing or melting. They'll just say the delta H for this process is either positive or negative. And from that, you should be able to infer whether or not it's freezing or melting or condensing and boiling. Please keep in mind that the energy required to freeze a substance is the same magnitude of energy required to melt it. They just have opposite signs, where one is losing energy and the other one's gaining energy. Same thing with the heat of vaporization. Positive delta H means that you are vaporizing something, going from a liquid to a gas state. Negative delta H means you're losing energy, so you're going to have some condensation, going from a gas to a liquid state. Again, the energy required to vaporize a substance is the same amount of energy required to condense it, just opposite signs. Now, the reason why the temperature does not change during these phase boundaries, or during a phase change, is that the energy that you're adding into the system or removing from the system is being used to either break or form the intermolecular forces, not to give the molecules more kinetic energy. So remember, temperature is defined as the average kinetic energy of the system. Well, the average kinetic energy does not change during these phase boundaries. All the energy changes involved are used on the intermolecular forces instead. Now, anytime you see this little degree symbol, it's actually pronounced not, which means this value is true under standard conditions. So that would be SATP, standard ambient temperature pressure, 101.3 kilopascals and 298.15 kelvins. Now, when it comes to chemical changes, that involves the rearrangement of atoms, and as such, you are changing the structure of the molecule, so you are creating a new substance. These energy changes are referred to as enthalpies of a reaction, or the heat of the reaction. Typically, you'll see it as delta HR or delta HRXN for reaction. Unlike physical changes where you are breaking and forming the intermolecular forces, with a chemical reaction you are breaking and forming chemical bonds. But other than that difference, all the other sign conventions are the same. So energy is required to break a bond, while energy is released while forming the bonds, positive, negative delta H. And the same magnitude but opposite signs still apply. With nuclear changes, we are focused on the loss or gain of nuclear particles, so those that are found inside the nucleus, and typically they will result in the atom's transformation into a different element. But we'll cover this later on in the video. But one thing to keep in mind is that quite often the mass of the products in a nuclear reaction is going to be less than that of the original atom. This is due to the lovely equation E equals mc squared, where the missing mass has been converted into energy according to Einstein's mass energy equivalence formula. In general, there are 3 different ways for us to represent enthalpy changes. The first 2 are using equations, and the third is with a diagram. In this first method over here, we write the energy values in the actual chemical equation itself. So on this side, the energy is written on the product side, so that means energy is being produced. If energy is being produced, it's being lost by the system, so it's going to be an exothermic reaction. So it gives off energy. It should have a negative delta H value. Over here, energy is written on the reactant side. Because it's on the reactant side, I require that energy for the reaction to proceed. So it must absorb energy for this reaction to proceed. So that's going to be a positive enthalpy value, making it an endothermic reaction. This is the method that makes the most sense to me when I'm trying to visualize the reaction. However, it's rarely written this way. Most textbooks and most questions will write the enthalpy values on the right-hand side like this, outside of the equation, and just tell you if it's a negative or a positive enthalpy value. Based on the sign, you should be able to infer whether the reaction is exothermic, giving off energy, losing energy, or endothermic, absorbing energy. Again, all reactions must absorb and release energy. It's just that overall, we're releasing more energy than we absorb over here, and absorbing more energy than we release over here. In the final method, we draw an enthalpy diagram to represent the change in energy during the chemical reaction. So this would be time or progression of the experiment itself. In this case, the reactants are turning into products, and over here, the reactants are less stable than the products. So energy is being lost by this chemical reaction, and that's why during the combustion of propane, it's very, very exothermic, gives off a lot of energy. In the process, you have unstable compounds like propane turning into more stable compounds like carbon dioxide and water. On the other hand, this one is going to be endothermic, so it's absorbing energy. We start off with a stable compound like water, and then by absorbing energy, it turns into these two products through electrolysis, producing hydrogen gas and oxygen gas, both of which are less stable than water. In this course, we'll be looking at three types of simple nuclear reactions, the first of which is alpha decay, or alpha particle emissions. So during this process, an alpha particle is ejected from the nucleus. An alpha particle is a helium nucleus, so that means it's 2 protons and 2 neutrons, no electrons involved. So if we look at radium, when it undergoes alpha decay, will eject helium nucleus, but in the process, because it loses 2 protons and 2 neutrons, it now turns into radon instead. Now, when we balance nuclear reactions, you have to make sure that the mass numbers balance on both sides, and the atomic numbers must also balance on both sides. So if you take a look at this, radium has 88 as an atomic number. On the other side, 86 plus 2 adds up to 88 as well. So that's balanced. The mass number must also balance out, so 226 over here, well 222 plus 4 adds up to 226. So let's try a sample question with uranium-238. When it undergoes alpha decay, what element does it turn into? So press pause. When you're ready, press play, and we'll take up the answer together. Alright, so the atomic numbers must balance on both sides. We have a 92 on this side and a 2 on this side, so the missing number must be 90. Looking at the periodic table, we see that thorium is element 90, so we write the symbol Th. Now, which isotope of thorium is it? We see a 238 on this side and a 4 on this side. In order to make this equal, the missing number for the mass number must be 234. Alright, so during alpha decay, uranium-238 will turn into thorium-234, and it releases the alpha particle, which is essentially the nucleus of a helium atom, no electrons involved. The next nuclear reaction we'll be looking at is called beta decay, so that's the beta particle emission. A beta particle is essentially an electron. Since the mass of an electron is very, very small in comparison to that of a proton or neutron, we assign 0 as its mass number. Because protons have a negative charge, we give it an atomic number of -1. Alright, so a beta particle is basically an electron. Again, when we balance the equation, you must make sure that the atomic numbers must equal on both sides, and the mass numbers must equal on both sides. So 3 plus 0 equals 3, 2 plus a -1 equals to a 1. So when tritium undergoes beta decay, it releases a beta particle, and it turns into helium-3. Now, a common question students will ask is, how is it possible for an electron to be ejected from the nucleus? I thought electrons exist outside of the nucleus itself. Well, that's because a neutron is converted into a proton and an electron in this process. So neutrons do exist in the nucleus, and in the process of breaking up this neutron, you create a proton and an electron, which is then ejected out of the nucleus. So that's your beta particle. So because you produce a new proton, you have created a new element, going from hydrogen in this case to helium, where you had 1 proton originally with a hydrogen, and now you have 2 protons for the helium. So let's try this example out. Press pause. When you're ready, press play. Alright, so I have a 31 on this side and a -1 on this side. That means my atomic number must be 32. Germanium has an atomic number of 32, so we write the symbol for germanium, Ge. Now the atomic number, or rather the mass number, must add up to 73. Well, it starts with a 0, so this one must also be 73. So during beta decay, gallium will eject an electron, a beta particle, turning into germanium, 73. Now, during alpha and beta particle emissions, the nucleus is left in an unstable or high energy state. As the nucleus relaxes into a lower energy state, it emits high amounts of energy. We call that energy gamma radiation. So that's the symbol gamma. Now, gamma radiation has neither mass nor charge, so we represent it as a gamma symbol with a 0, 0, or simply just the gamma symbol. All right, so in this case over here, this is an example of a beta emission because it's releasing or emitting a beta particle. Anytime you have beta decay or alpha decay, it's always good to write down gamma radiation as well as being released. In the process from, in this case, cesium turning into barium, it's relaxing into a more stable state, and it must give off that energy in order to become more stable. Now, nuclear fission occurs when a highly unstable isotope is split into smaller particles, so you're breaking apart. During this process, you release a lot of energy, and it's normally induced inside a particle accelerator. So high energy particles, such as neutrons, collide with unstable isotopes, causing them to split into smaller particles. So let's take a look at this example over here. Uranium-235, and then we're going to fire a neutron at it. In the process, bromine-87 is produced, and 3 other neutrons are fired out as well, ejected from this nucleus. So what is the missing element in this particular equation? Press pause, and when you're ready, press play. Alright, so you should have lanthanum-146. A common mistake students will make is they'll forget that it's 1 plus 235 equals 236 at the top. But don't forget that there's 3 neutrons being fired out, so it's got to be 3 times 1 plus the 146 plus the 87 should add up to 236. Now the opposite of nuclear fission is nuclear fusion. So instead of splitting an atom, we are now fusing them together instead. Alright, so it occurs when a nucleus absorbs an accelerated particle. This requires very high temperatures to proceed, but produces enormous amounts of energy as well. So in this example, lithium-6 fuses with 1 neutron to form hydrogen-3 and helium-4. Again, 3 plus 4 equals 7, 1 and 6. 3 plus 0 adds up to 1 and 2.